Given the tradition established by the first speaker, I have to also start by apologizing that I will not be speaking about representations with p-adic or mod p coefficients, but still about.
What is the title of this? Is this and or? Maybe Galois representation or.
Okay, that would certainly give me some more room. So what I want to talk about is I want to talk about the structure of L packets on general reductive groups, and in particular emphasize the case where the group is not quasi-split, which is somehow the case where a certain fuzziness occurs, and the question is how is this fuzziness resolved and how can one get a clean picture. And this will involve the theory of isocrystals with additional structure developed by Kottwitz. And so my talk will have roughly 2 parts. In the beginning, I'll try to motivate the problem and state a precise conjecture. And this is the first half. And in the second half, I'd like to say something about results towards this conjecture. So let's get started with some notation. So F will be a p-adic field with a ring of integers. And I may need a uniformizer. I'll denote by K sub F the residue field. And then we'll have the Galois group, F bar over F, Weil group, inertia, and wild inertia. And then I'll take G to be connected reductive group over F. And I'd like to just start by recalling something that's known to everybody, but just to set the stage. I'd like to recall the local lines correspondence for discrete series representations and for quasi-split groups, or maybe in the beginning just in general. So let's just recall what a discrete Langlands parameter is going to be. It's going to be a continuous map like this from the Weil group times SO2C going into the Weil form of the L group for G, respecting the corresponding projections to the Weil group and respecting the Jordan decomposition on both sides, where here everybody's semi-simple. This one has its usual Jordan decomposition. And here we can look at a quotient of this group to a group like this, where we take semi-direct product with the Galois group of some finite extension K, which splits G. And this is now a complex algebraic group. It has its usual Jordan decomposition, and we lift this Jordan decomposition to elements here. And so those things, if I didn't forget anything, this is the notion of a Langlands parameter. And we're going to use this group over and over again, so I'm going to give it a name right now, which is a centralizer of the image of the Langlands parameter in G hat. And this group naturally contains the Galois fixed points of the center of the dual group, and we call phi elliptic if this containment is a finite index. So and so the conjecture is that we parameterize packets of discrete series by objects of this kind up to conjugation. So we have phi up to conjugation on the one hand, and discrete series L packets on G of F on the other hand. And so now this should work for any G, quasi-split or not. But the question is now, given an L packet, how is its internal structure parameterized? How are the individual components of this L packet parameterized? And so I would like to recall again the case of the quasi-split form, which is where this conjecture has been out there for a long time. But I want to recall, the reason I want to recall it is because I want to pinpoint that already there it's a certain question arises as to this parameterization, and I want to draw it in connection to transfer factors. And this is going to give us the lead to what is the problem when the group is not quasi-split. And so the internal structure in the quasi-split case, where, well, it's very simple. There, one expects to have a bijection of this kind. So that's it. One expects. So this is a finite group because the parameter is discrete, and we expect that irreducible representations of this finite group are in bijection with this packet here. Now, what is the problem? Well, did I so a bijection. So one thing that one often says is, well, there is the irreducible representation here. It is a base point, so we have to have a base point here. How do we find the base point? And this has to do with Whittaker data, but I want to say the same thing with a little bit different words, which so here are my different words. Now let's say we have an element in this group. Let's take this element S in this group. And now if we have a bijection, I want to give this did I give this bijection a name? The name of this bijection is rho goes to pi sub rho. So if we have a bijection like that, then what can we do? Well, on the one hand, we can form this endoscopic linear combination of characters in the L packet, which is going to be the sum over rho, trace rho of S, and then the character of pi rho. So this is one thing. And on the other hand, what we can form is, from S and phi, there is a recipe which tells you how to form an endoscopic group, or more generally an endoscopic datum, and moreover, a Langlands parameter for this endoscopic group. And from this, what we can do is we can form the stable character. And I want to lie a little bit and just pretend that this is simply the sum of representations, maybe H like that, where now, well, so I'm just summing over characters of representations in the corresponding packet for H, which one gets from this. And of course, one is not supposed to sum in general, or just pretend that one just sums, because I want to get to the point. And the point is the following. One expects to have the following identity, that if we evaluate this character thought of as a distribution on some function f, then this is the same as evaluating the stable character on the endoscopic transfer of f. And this identity is the identity that is now going to tell us why such a bijection, why is there a problem, why such a bijection cannot be unique. Well, the point is that this correspondence of functions, so fh is not well defined as a function, but its stable orbital integrals are well defined given f. But this correspondence depends on Langlands Shellstadt transfer factor, which is a function from, well, it takes pairs of elements, so f is our local field, and these are supposed to be sufficiently regular, these are supposed to be sufficiently regular, and it gives us an element in C. And the point is that this function is just, if we take h and g and the corresponding data that comes with this h, is only defined up to a constant, a non-zero complex constant. And why is that a problem? Well, if we change this constant by, so we have to choose a normalization, different normalizations differ by a constant. Every time we choose a particular normalization, when we change it, what we change is this f upper h up to the same constant. So this depends on the choice of delta. Here, nothing depends on the choice of delta. On the other hand, if we change our bijection, rho pi rho, then this side changes. So this depends on the bijection rho goes to pi rho. And so you see that normalizations of this bijection and normalizations of the transfer factor are two sides of the same coin. And so you cannot expect to have a bijection canonically given like that, given the fact that there is no canonical transfer factor. Or to say it even more precisely, if you want to have something that pinpoints this bijection, it better be something that pinpoints this transfer factor. And so given that we're in the quasi-split case, it is well known what helps in both situations, namely that's so we are in the quasi-split case. So what helps is a choice of a Whittaker datum, which is a pair B, say psi, where B is a Borel of G defined over F, and psi is a character of the unipotent radical of this Borel, which is generic. Now, given such a pair, first of all, there is a canonical normalization of the transfer factor, the so-called Whittaker normalization. So from this, we get two things. One is the Whittaker normalization with respect to this Whittaker datum, which was defined by Kottwitz and Schellstadt. And on the other hand, we get a restriction on the kinds of bijection we may have up there. Namely, they have to be bijections. So they have to be bijections which send 1 to a pi sub 1, which is the generic representation with respect to that particular Whittaker datum. Generic. And it's one of the conjectures involving alpacas that there should be exactly one such generic representation given this Whittaker datum. I'm not entirely sure whether this condition is supposed to pinpoint only one such bijection, but it will be the case that in the results that we'll be talking about in the second half of the talk, this is what happens. That once you fix this, there will be a canonical bijection of this kind. So this is as far as the quasi-split case is concerned. So now let's look at inner forms. So again, is that a good board to use from over there, or should I stick to the central ones? That's okay? Okay. So let's look at now internal structure. And by internal structure, I just mean a bijection of this kind, describing the components of an L packet in objects related to the dual group. Internal structure in the case of inner forms. Okay. And so now that we've had this discussion, it is natural to say, but wait a minute. First of all, you're running into the same problem. You have to normalize the transfer factor now for an endoscopic group in a given inner form of G. So let's say if G is not quasi-split, we can realize it as an inner twist of some quasi-split group G0. So this guy will be quasi-split. And now we'll be having endoscopic data for G or G0. That's the same thing. And then transfer factors for a given endoscopic datum and a given G. And again, we'll have to normalize them somehow before we can hope for this. But the trouble is there is no normalization without fixing additional data, just like in this case. So what additional data can one fix to do this? Well, the first idea, I guess, was Vaughan's pure inner forms, where in addition to the datum of which realizes G as an inner twist of G0, one takes yet another element. So this will be a rigidifier or a pure inner form, where this is the rigidification datum, the Z. And the Z is supposed to be a one co-cycle of the Galois group in G0, and it's supposed to realize the following. So let me just write this. So for any element in the Galois group, this is supposed to be an inner automorphism of G0, and this inner automorphism is supposed to be realized by this element here. So this is the condition on this triple. And this works well, but the trouble is that this is not simply a rigidification. That is, the existence of such a z puts a condition on this tuple, and not every tuple.
Is z0 the same as z?
That's a z sigma. Sorry, that's the value at sigma of z.
Sorry.
No, thank you. So the worst case is where G0 is simply connected, then no inner form will have such a Z. So, OK, so what else can we do? Well, the second idea is use the set B of G sub 0, which is the set of isocrystals with additional structure associated to G0. Maybe I'll just spend a few words describing what this set is. First of all, we can, well, let's say that L is the completion of the maximal ramified extension, and L bar will be some algebraic closure of L. Then we can describe this set in just cohomological terms as being cohomology. Maybe I wanted to say that. If we look at the continuous automorphisms of L bar over F, then those are going to be just the Galois group of F. So the action of the Galois group on F bar over F extends to continuous automorphisms of L bar over F, and the fixed field is again F. So we can look at cohomology of the Weil group in the points of G0 with coefficients in L bar.
Kind of a motivational question.
Yeah.
Just in the case of real groups, is there something that's kind of completely understood in this case, which one is not trying to emulate? Okay.
Well, I'm pretty sure there are people in this audience which are much more qualified to answer this question. But the
same problem must arise.
The same problem arises there as well, but somehow the theory of real groups has developed a little bit different than the theory of the periodic groups, in the sense that where is it still on the board? Oh, this thing. So Shellstad defines, rather than using this, a much more elaborate theory of spectral transfer factors. And these spectral transfer factors can again be chosen up to a constant. And so one has a leeway there of putting constants, which are all that we are worrying about, renormalizing things up to a constant. And so the theory is developed from that point of view. And then there is also Whittaker normalization. And so I think the problem arises there as well. You can use pure inner forms, which are those things there as well, if you want to stick to expressions of this kind. But this, of course, will be something that is not visible there.
Can I ask just one more question?
Sure.
While you're looking at that part before. In the sum for the stable model group,
Uh-huh.
is over pi in, is over little pi in pi h phi h?
Right.
That phi is
That's a sloppiness on my part. Thank you.
I'm sorry, just one more question. You are saying that the automorphisms of L bar over F continuous
Yes.
are the standard Galois group?
Yes.
Okay. I
Yes.
suppose that's well known.
Yes, I think so. And moreover, if you like, the automorphisms of L over F, these are just the unramified Galois group, which I want to call Frobenius by sigma. And so one can just write this down as in this way, just cohomology of this group. This is Z with values in here. And this has a completely down-to-earth description. We're just looking at elements, L points of G0 up to twisted conjugacy by Frobenius. So one can describe this set in a very down-to-earth way, but to each such element, we want to associate its Newton point, and that's something that is not immediately visible from this point of view. Maybe, even though I'm running the risk of boring people in the audience, I want to just say what this is. So if we look at this set in the case of GLN, what we end up getting is, well, if we take an element like this, which I'm now interpreted. I'm saying this will be sigma conjugacy classes in the L points of GLN, but let's take a particular representative. So from this, we can build the following object, the n-dimensional vector space over L, and then G sigma. And this gives us an isocrystal in the usual sense. This is an isocrystal in the usual sense. And moreover, the isomorphism class of this isocrystal is not going to depend on the particular representative I chose in the sigma conjugacy class. And then the Dieudonné-Manin theory tells you that any such object decomposes as a direct sum of simple objects. And the simple objects are parameterized by rational numbers. Ri over Si, I'm writing this as a reduced fraction. And any such isocrystal is an L vector space has dimension Si. So this isocrystal is described up to isomorphism by just the tuple of these Q numbers, where I take each number Ri over Si, I repeat Si many times. And this ends up being in Q to the n, which I can interpret by just basic linear algebra. I can write it in this way. And now the final thing, so we get from such an element, we get a homomorphism. And this is the prodiagonalizable group with character group Q. And I get a homomorphism from this group into that group, which I can continue into G. And the whole procedure gives us the Newton map of the isocrystal, which is a map like that. And so I went through this whole description just so that I can now say the following words. Well, if we have a general quasi-split group G0, we look at all its rational representations at the same time, get a compatible system of this Newton map, and the Tanakian formalism gives us, for a B now in general, for general G0, we obtain a map like this, defined over L. And this map is what is used to define a subset of this set of basic isocrystals, which are those B for which this map factors through the center. And in the particular case of GLN, those will be precisely those isocrystals which are isotypic, where there is only one simple component occurring many times. And the point is now that these things are useful in two ways. So if you take an element from here, there are two things we can do with it. One, and I want to just say that we can do it without saying how we can do it. So this element can be used to extend any normalization of the transfer factor for H in the quasi-split form G0 to a unique normalization of the transfer factor for H and this inner form G, which be, I guess I got ahead of myself. I should have made this arrow be up and this arrow be down, because I wanted to say that B provides an inner form. So the one thing is B provides an inner form of G0, and this inner form, so this is a construction, I guess the names attached to it are Kottwitz and Rappaport and Zink. So this inner form, let's call it J. Instead of saying how it is defined as an algebraic group, I'll just say that its F points are horrible G. are the sigma centralizer of this element B in the L points of G. If you look at the sigma centralizer of this element, then those are the F points of this inner form. And the basic condition here is needed because if we do the same construction for a non-basic element, we'll get an inner form of a Levy. The basic ones are the ones that give you an inner form of G0. And now that we have this inner form, we can also use the B to do this. Namely, given any normalization of the transfer factor for G0 and H, we get a unique normalization of the transfer factor for G and H. Mm-hmm.
B is equal to J?
Sorry, yes, that was the, thank you. G is equal to J. So these elements B, because they have the capacity of providing normalizations for transfer factors, we have a hope of them having the capacity to also provide us with bijections like this. And so let me just write down what the conjectural expectation is.
What does extend exactly mean?
What does
Extend.
well,
It's not like you're literally extending to a larger set.
exactly. This is what we're doing. So, okay, I'll say what this means. This has to do with viewing L packets on different inner forms as somehow this super L packet sitting on all inner forms put together. This is a very important question that I wanted to discuss. Yes and no. So yes in parentheses. But I'll say precisely what this means. So extend means, well, let me, instead of looking at a huge union of inner forms, let me just look at the quasi-split inner form and the one given here, just the two. Let me look at this union. It makes sense to say what it means for an element in here and an element in here to be stably conjugate. And so this makes sense even before rigidifying or anything. It is enough that one has this inner twist and one does the very obvious thing. One just puts the element gamma through this inner twist in here. It's not going to be an F point anymore. It will be an F bar point, but you can still ask whether or not it is conjugate to this element. And in this way, you can extend stable classes. You can also extend rational classes in this way to accommodate B's, which give you the same inner form, but just rigidified in different ways. So you can extend the notion of stable classes, extend the notion of rational classes, and then you can look at transfer factors. And transfer factors, just on one group, are supposed to have the following property, that they tend to have a property of what happens when you vary the second argument.
I'm sorry, just a question here. You are thinking of semi-simple elements, semi-simple regular?
I'm thinking of semi-simple elements which are as regular as they should be. Yes, yes, yes. Thank you. So whichever transfer factor we're looking at, it's supposed to have this kappa behavior with respect to the second argument, which means that it's supposed to gamma prime, and then S. It's supposed to, when you change its second argument within the stable class, you're supposed to get out the endoscopic character paired with the invariant, which measures the relative position. And the point of this B is that now you can make sense of relative position of an element in here and an element in here. And then you can require to have a function like this, which lives which in the second argument takes an element from this union, and which still has this invariance property. And now a theorem of Steinberg tells you that any element here is stably conjugate to an element here. And so once you know this and you have picked a specific normalization of this, it's just a matter of defining this. And in here is where B enters to define this invariant. And without the B, you will not have this invariant. And if you take two different B's which give you the same inner form, these invariants will be different. So from the point of view of the invariants, the forms will be different. So this is what extend means. And now I just
There is no base point here.
a choice of psi. Psi is chosen. So so what we're let's see. Huh? Psi comes from B. Right. So once you choose B, psi is given to you.
So
Once B is given, you're done. So if you want to write things completely precisely, then you want to choose your B to be a representative of such a cohomology class rather than the cohomology class itself. But when you start doing things, you'll see that varying it within its class doesn't make a difference. But if you want to completely pinpoint everything, the B is like this. OK, so here is the conjecture, which is largely due to Kottwitz. And then, so the first part is, let's make sure I don't write anything wrong. So the first part is the following. Let's consider the irreducible representations of this group. Now, one may need to be a little careful by what this means, because this group will be infinite in general. But this group is finite modulo its center. And so we can think of irreducible representations whose restriction to the center, which is a complex diagonalizable group, is algebraic. And those are the representations that we're interested in. We can restrict them to algebraic characters of this. And now Kottwitz provides an isomorphism, or a bijection, between this and this set. And we can, every time we're given a B in this set, we can look at the fiber of this map over that B. And so the fiber over B is in bijection with this L packet. Okay, so every B is going to give us an inner form, a packet on this inner form. And maybe I should literally write G or J comma psi comma B to emphasize the fact that different J's which are the same from the point of view of inner forms, when you put different B's, you should think of this packet as a different packet. I'm sorry. I want to write this out to make sure that this little b is not the same as that little b. Yes. Subscript stands for basic. The second thing is that, well, let's see how I numbered them. OK. So the second thing is that the following function, which you can now form, you're looking at all rows in this fiber. So they're supposed to parameterize this L packet. And you're taking their dimension times the character, that this function is supposed to be stable. And this EG here is the Kottwitz sign of the group. It, of course, when you formulate this, it doesn't play any role. I mean, the function will be stable no matter what constant you put in it, but it will play a role in number 3 downstairs. So this is stable. And the reason I put this sign here is because I want to connect it with this notation. And the first point, and the third point, is that this is a sum over row in the fiber of this map over B. So maybe I can write this down as like that, row mapping to B. And the third point is that now we can form. So if we form the same alternating sum as before, which got erased, I guess, we prepend this sign of G, and then we do the same time as for the same sum as for the stable character, but we put trace row S in front of it. That if we form this sum, then we're supposed to have an equality of this kind, where now nothing is fuzzy anymore, because to get FR per H out of F, for one fixed Whittaker datum. We have the Whittaker normalization of the quasi-split form. We extend it by this B. Now we have a unique transfer factor. We take the F upper H with respect to this transfer factor. And moreover, on this side, we still demand that on the quasi-split form, the trivial representation goes to the unique generic representation. So now everything is fixed. Sorry. Where is it? Here? Oh, E of G. In the p-adic case, E of G is simply -1 to the difference between the split rank of G0 and the split rank of G.
So G's again J.
G's. All right, how about this? I'm sorry,
Actually, I think in this theta it is a B, not a J.
in this theta it is a.
Because so much like G that everybody thinks it's a G.
Yes, I've been told this, and I somehow failed to take this to heart. Please ask me if anything is unreadable. And there is a 3' here, which occurs when you take B's where the corresponding G or J is, what do I want to say? There is a 3' where the endoscopic group that you're looking at is G0 itself. So you're comparing you're comparing this thing, which is now going to be for S equals 1, the stable character on the inner form against the stable character on the quasi-split inner form. And what this ends up being is the old expectation that you're supposed to have the stable character. Let me write of them now as functions rather than distributions. So the stable character on G0 is supposed to be equal to the stable character on G or J whenever gamma and gamma prime are stably conjugate. And you see, this is what this sign was originally made for, to measure sign differences when you change inner forms and compare stable characters. All right, so this is as far as the conjectural description is concerned. I want to say now a few words about what we know. And I want to discuss 3 cases of 3 different classes of parameters and say what is known in each case. So the first case I want to call the Terselp case. And here G0 is an unramified group, and phi is an elliptic parameter which is subject to the following 2 conditions. First of all, if you plug an element in the wild inertia, the thing is trivial. So this is what the T is. And the second 2 are regular semi-simple, which means the centralizer of the image the centralizer of the image of inertia in G hat is a maximal torus. Okay, so those are the 2 conditions, and we already assumed that phi is elliptic. So in this case, the full conjecture is known, but with the caveat that stability and endoscopy are known for P large.
In the conjecture, let's assume G0 is unramified?
No.
So it's general.
No, the conjecture does not have the assumption of G0 unramified. This is the particular case here, that we take G0 unramified. So this is work of Debacker and Reeder, who did it for the pure inner forms, who did construction of L packets into internal structure and stability in the case of pure uniforms. And then that was extended by myself to the general class of uniforms and to endoscopy. In the second case, I want to call RSELP, which on the Galois side looks kind of analogous to the TRSELP. And so G is again unramified. And now instead of requiring that this thing is trivial on wild inertia, it will be trivial on a certain higher filtration subgroup of inertia. So there exists an integer n such that the same thing holds for W in this filtration subgroup, and then we get the same condition here, but now we put the next bigger subgroup here. Okay, so what is known in this case? In this case, the L packets and internal structure are basically known due to, well, so L packets are known due to reader and myself, again, the extension to the larger class of uniforms. Stability is underway. This is the Barker and Spice. And then endoscopy makes no sense to look at if you don't have stability. And then the third case. So I want to maybe emphasize that although on the Galois side things look very analogous, on the representation theoretic side the representations involved are entirely different. Their construction and the way they come about, at least from the point of view I'm looking at, don't have anything to do with each other.
Well, you're saying you constructed representations and you postulate that they're the ones that correspond to the parameters.
Exactly. So we're hopeful, but hope somehow comes from here and here. So first of all, as far as I understand, for real groups, L packets are characterized by something called atomic stability, which means that if you sum their characters, you get something stable, and no subset of them has this condition. Well, you have this here, so at least you have some certainty that you've constructed the right L packets. Maybe you haven't matched them in a good way with the Galois side, but then endoscopy kind of speaks against that, because it appears that if you have a mismatch on the Galois side, you should see this because you're looking at different groups with different parameters, and then you're supposed to compare the characters.
So what structure do you use to construct the representation? Do you use types?
So I'll say something about it right now because I wanted to just write down the third case and then talk about how things are done, so give examples. And they're done in different ways, in the different cases. And in fact, this will be somehow the base case. If you look at JKU's construction, he starts with the depth 0 supercuspidal representation and then pulls up. So this is what comes here. And here, there are things somehow in this pull-up. And in fact, when you do the thing here, you start with a trivial depth 0 representation. So it's somehow even orthogonal, somehow representation theoretically to this. And as far as I understand, for groups other than GLN, you just don't have anything better than this hope and endoscopy. Hope maybe twisted endoscopy, but you don't have epsilon and L factors to say exactly, oh, I did the right thing. The only way to say it is when you exhaust all representations and you get compatibilities in the way you like. Right. Okay.
So this is my next one. Is it conceivable that sort of the stability endoscopy statements somehow imply uniqueness or something?
Imply
A kind of uniqueness.
Uniqueness.
Is that conceivable or
They certainly give you strong restrictions on what you can do. I'm not entirely sure that they would give you uniqueness. I can imagine that there are certain kinds of non-uniqueness which are somehow naive, that you can twist things around by something. I don't know. But whether aside from that you get uniqueness, I just don't know. But I mean, but you know, if you feel happy by pulling information from GLN to other groups using endoscopy, then maybe you trust endoscopy so much that you're willing to bet that an L packet coming from endoscopy is the right thing and the right parameterization. So here you have it. Endoscopy works. And the third case is the simple wild case of Gross and Reader, where the conditions now look quite different. The first condition is that when you look at the adjoint action of this parameter on the dual Lie algebra, this has no invariance. And the second condition is that, well, you're looking at this action, you look at its one conductor. Now I guess it's horrible to write B again because B was overused, but that's the notation they use. That this equals to this is equal to the rank of G, and here I mean the absolute rank. So maybe I'll just put rank of G hat. And so in this case, what is known where, well, I have to assume, I have to put the same assumption as Gross and Reader put in their paper for now, which means that this is split, simple, and simply connected. But I don't think this is an important assumption. They put it so that they can write down clean formulas and explain their point of view. But split and simply connected certainly can be disposed with right away. I'm not sure about simple because they they have ideas of what to do when they have different irreducible root systems of different types put together. But I'm pretty sure that those are not really a problem. And then L packets and stability are known. This is recent of myself, and then endoscopy is underway.
So if I remember correctly, like in their work, at least when the prime was so small, one thing was they constructed representations, and it wasn't so obvious how to make it fit.
Right.
Are you addressing that issue, or do you assume
No, I'm not addressing this issue at all. So what I'm assuming is that P does not divide the Coxeter element of the group, which is a little less weak as what they assume, but that's somehow cheating because they give a different characterization of these parameters in the case where P doesn't divide the order of the Weyl group. And I'm taking this equivalent characterization and imposing this weaker condition and constructing all these things. And if P satisfies this condition, but it still divides the Weyl order, then everything works that I do, but it's just not said that I exhaust all parameters of this kind. So their equivalence of descriptions works when P doesn't divide the Weyl group. Otherwise, the other description becomes not equivalent, but a subset. And so with this other subset and this assumption, this can be done.
But you don't have to construct these bizarre parameters.
No, I don't have to construct them, although I'd be very interested in constructing them. But the first step was to take what was easiest and most immediately accessible and try and see what happens with that. So now, in the last 10 minutes, I want to say, yes?
Does Collins have a more general conjecture that deals with the problem of grossly disconnected center?
Well, I haven't come to talking about centers connected or disconnected at all. But I will do this before my time runs out, because this is what Yanis was asking about. This was where somehow the disgrace of this thing shows up a little bit. So I want to say a few words about how these things are done, and then go into discussing in which cases isocrystals do rigidify all inner forms, and in which cases they don't, and what would one do then. Okay, so I want to say a little bit about the methods. And the first thing I want to say is this is factoring of parameters through L groups of tori. So in some sense, if you like, the L packets that we're looking at are the dihedral L packets in the sense of Langlands. These are those which come functorially from L embeddings of tori. And why is that? Well, in 1 and 2 it's obvious, and in 3 it's obvious if you look at the alternative description that Gross and Reader give you, that the parameter picks out for you a unique maximal torus in the dual group. So phi picks a unique t hat. So in this sense, it behaves very much like a discrete series for real groups. Parameter picks for you a unique maximal torus, and moreover, it doesn't just pick it out, but it factors through the normalizer of this torus in G hat. So this is what you get. And what you want to do is you want to really realize this parameter as something continued from the L group but of which torus? Well, you project this down to the Weyl group. This is an F. And now by duality, this is just the Weyl group of your quasi-split torus in G. And so you get an element in H1, Galois, and then the Weyl group. And this element, just by the basic structure theory, provides you, first of all, a torus, and then a stable class of embeddings of your torus into G, or let's say G0. So it provides you a certain torus. It has a rational structure. The rational structure has nothing to do with this quasi-split torus. It's a twist given by this element. And moreover, it gives a stable class of embeddings like that. And now dually, what you obtain is a conjugacy class of embeddings like that. And you'd like to extend these, but somehow on the dual side, conjugacy, you take everything up to conjugacy. So you basically get a good object on the dual side, and you'd like to extend this into an embedding of the L group of this torus into the L group of G0. And in order to, and embeddings like this are fundamental in the construction of transfer factors, and so Langlands and Shellstad have given a way to do this, and their argument depends on the choice of chi data. This is additional datum that you need to pick in order to make such an embedding. And moreover, this embedding is going to depend heavily on this chi datum that you pick. So you have to be careful how you pick it. But let's say we pick one, and then once we do this, we have a diagram of this kind pretty much tautologically. That is, you get to factor your original parameter through this L group of your torus. And so what you end up getting is a torus together with a character on it up to conjugation by F points in the Weyl group of that torus. Now this group does not depend on how you put your torus, does not depend on the stable embedding you chose for your torus in G. And so you get a torus, you get a stable class of embeddings into G, and you get such a orbit of characters. And now you have to worry about dependence on the choice of chi data, and in the different cases, this is somehow done differently. Maybe I want to describe, just to give a flavor, the third case. So in 3, I want to give an example of what is happening. So in 3, this torus is inertially anisotropic, which means that even if its base change to the maximum ramified extension stays an anisotropic torus. And now you can look at, and one of the things this means is that you have an error model for this thing. And now the F points of this torus, they have a natural filtration, the so-called Moy-Prasad filtration, which is indexed by non-negative real numbers, is descending. And this first filtration step, you take the connected component of the neuron model and you take its OF points. And and the other thing is that it is tamely ramified. And so given that this torus is tamely ramified, the natural class of chi data to pick are so-called tamely ramified chi data. And all this means is that when you use the arguments of Langlands and Shellstadt, they tell you that when you change the choice of chi data, this character here is going to change by multiplication by a tamely ramified character. And so your job is to see that this tamely ramified character is in fact trivial. And the way you see this is by studying this filtration, which amounts to studying the special fiber of the corresponding neuron model. And what you get out of this is the fact that, first of all, this step here is in fact no step, which means that this group here is a subgroup of this group defined by congruence conditions, and you end up showing that already the OF points of this connected neuron model satisfy this congruence condition by themselves. And from this, with a little more work, you show a decomposition of this kind. And now a tamely ramified character is a character which vanishes here. And on the other hand, these correction characters, when you change chi data, are always trivial on the center, and then you're done. So this is the kind of thing that somehow goes together with this factoring of parameters and choosing embeddings like this. So although the embedding is not going to be this L embedding, well, no, I don't want to say this. Something else I want to say. Okay, I wanted to say something about the representations which are involved, but given that I basically exhausted my time, maybe I'll just say it in words. So the representations involved in the different cases are quite different. So the way you go about here is from the torus in case 1, which is again an elliptic torus that provides you a point in the reduced building of G. This point ends up being a vertex. You look at the corresponding group over the finite field of its reductive quotient. This torus gives you an elliptic torus in this group over the finite field. And moreover, the character that you end up getting is a character which provides a character of this torus over the finite field, because it's tamely ramified again. So it kills whatever you have to kill in order to do the reduction. Then the Leon-Lustig induction gives you a representation of a cuspidal representation of this group over the finite field. There is a technicality that this is a character in general position, so you really get an honest irreducible representation of the group. You inflate that representation to the full parahoric. Maybe you have to marry it with something on the center, depending on if you have a center, and then you induce. So you have a depth 0 supercuspidal representation. This is in case 1. Case 2 I want to skip. And case 3, what you do there is something completely different. The torus again gives you an element in this building, but this element is not a vertex anymore. In fact, it is a barycenter of an alcove, so it provides you with an Iwahori. You have an Iwahori, and it comes with its own filtration, and you also get an embedding like this. And the point is to extend the character you have on here to a character on here. One can do this canonically. And then this is precisely the data that from which Gross and Reader provide you with a simple supercuspidal representation. And then you have to put them into L packets, which is again in the case 1 and 3, it has certain similarities and certain differences to it. And I wanted to talk about it, but I guess I've run out of time. What I wanted to tell you is how, now that you know what the representations are, how do you put them together into an L packet and do the internal parameterization? And this is something I like a lot, but I guess I don't have time to talk about it. So. Can I ask the first question? Yes. I remember that I forgot to do justice to the questions already asked, namely the trouble with centers, and why can you not always rigidify all inner forms? I wanted to have said this, and it is the following problem. So you have these elements. They're going to provide inner forms for you, and you have just from basic constructions, this association is functorial. So you have a map to the adjoint group. And well, what are basic elements? Those are those whose Newton map factors to the center. There is no center here, so then their Newton map is trivial. And the general theory then tells you that those are precisely the things which come from usual Galois cohomology. So this is another way of seeing inner forms produced from this. And the question is now, is this map surjective or not? And the answer is this is surjective if the center of G, or G0, is connected. Now this sounds horrible, right? Because, well, let's take the worst case scenario for pure inner forms, where the group is simply connected. Then you don't have any pure inner forms. But then you have the theorem that this is also trivial in that case. So if you just stop looking here, it appears that you gain nothing at all. But the point is that you can always make the center connected, make connected, whereas you cannot always make it disappear so as to make the pure inner forms work. But there is a caveat with this, that you shouldn't just do the basic dual Z extension, because you then destroy endoscopy. In particular, if you put SLN in GLN, then you lost everything. But there is a way to put any group, to fatten it up in such a way that the center is connected, but moreover to preserve endoscopy. And then once you do this, then you're in business with this construction. But it's a certain cosmetic defect with this, and maybe there is a better construction which works even with disconnected centers. But I don't know of it yet. So just wanted to put this out.
You have to enlarge the category of groups, like you can't do this in the category of unramified groups?
Right. So one thing that happens is when you fatten up your group, the center will be ramified. So even if your group was split, or if it was unramified, the center will be ramified. This is not going to pose troubles for you if you use Bruhat-Titz theory, because the reduced building won't change. But still, there will be something changing in the center.
Can you tell from SLN?
I don't think it has a name, but what you have to do is you have to make sure that whatever you do, Galois cohomology of the center of your group, let's call the new group with a twiddle, then this has to be in bijection with Galois cohomology in the center, in this fattened center. And this is why this center ends up being ramified. I mean, I guess, I don't know if it's immediately visible from here, but if you start constructing this and look at what local class theory tells you, you see that you have to ramify it.
So you are saying that your Z extensions don't work?
No, yes. Or they're dual somehow. The dual construction, yeah, it doesn't work.
I have two questions. First, in the case of GLN,
Mm-hmm.
the analog of this, it's well known that there's a natural way to construct a bijection between representations and the tame parameters.
The naive bijection. Right.
Unramified character. You take that into account? Because I don't think it's even been solved completely.
Right. So this is something that I was unaware of in the beginning. And so I'm taking this into account in case 3 now. So case 3 so far is done for simply connected groups, and I'm extending it to reductive groups. But in this extension, one has to take this into account, and I'm computing now. So I don't know what will come out, but whatever comes out, we'll have to go into that.
So the other question is, if you have a basic datum, and if you believe there's a rapport sync space attached to it, that has an action of the group, the two groups G and J, and looking at the cohomology, there's a way to go from representations of one to representation, or at least on one probability groups, which dually gives you a transfer map on functions.
Mm-hmm.
But it seemed natural to guess that transfer map is the one that comes from your B.
It seems very natural, but I have no wise words to say on that. I just haven't looked at it yet. So, but I'll be very happy to look at it. Yeah.
classification of discrete series. Do they do that only for quasi-split groups, or are there other cases?
I don't know. I don't know this.
The second question is, there will be cases where, you take an inner form. For one packet, you have representations which contain the ligne Veil SL2. But because the other group is more compact, this is not the case there.
Mm-hmm.
Do you encounter this kind of example?
So this is something I wanted to have said, and I guess I completely forgot about it in the heat of the battle. And that is, I wanted to say just one additional sentence to the beginning where I recall the discrete correspondence, where you have discrete parameters going to discrete L packets. And so as far as I understand, it's a complicated question to know when in a discrete packet you have supercuspidals and non-supercuspidals and how they come together. But conjecturally, it's very clear to know when you have only supercuspidal representations. And this is precisely when SO2 is killed by the parameter. And in all three cases, this is what I'm looking at. I'm looking at parameters which kill SO2, so they correspond. Yes, so they correspond to packets which contain only supercuspidal representations. So I guess the examples I'm looking at are not relevant to your question.
But it would be quite interesting to make one computation where you have an SL2 and quasi-split. Because these examples are classified. It's complicated.
Mm-hmm. Yes, no, thank you. I'll look into that.
Well, if there are no more questions, let's thank the speaker again.